Hello everyone, I'm Mike. I'm a PhD student in brain-computer interfaces, and this is the first video on my series on analyzing EEG data. So in this video, we will see how to analyze data containing the P300, a very well-known event-related potential in the field of neuroscience and, of course, brain-computer interfaces. So this task has been done countless times, and it's usually the perfect task for beginners to understand how this mechanism work in the brain, but also for building a BCI. It's also not so trivial. So there are many tools that can be used, many type of devices to record the data, many programming languages, and it can be overwhelming for a beginner to just get started. And especially if you find yourself struggling in understanding what's going wrong with your data, this is the video for you. So I will also give you tips and tricks that I wish somebody gave me when I started. So I hope this will be really helpful in getting you started. And you will find all the code for this and the next videos in my GitHub, which is linked in the description. You can use the code with my own data, try it, understand it, and when you're feeling more confident, you can just load your own data and get started with your project. All right, so when you open the notebook, the first thing you should do is import in the libraries. If you open this in Colab, so from my GitHub, there is a link, a button for opening in Colab. You have to first run this command for installing the MNE library. And also you have to make sure that the data are loaded from your Google Drive. So the data in the repository will not be taken in consideration by Colab. Also, the second thing, for the first part, I want to show you interactive plotting. So for this, you need the library PyQt5 or PyQt6. I'm using PyQt5 here. And the main reason for interactive plotting is that MNE as a library has some extra functions for these plots that can be applied to your data. So it's more convenient for you to understand and to use these tools. So MNE is a library in Python that can be used for analyzing EEG and MEG and other type of biosignals. The library is very well maintained, documented, and it's widely used in the field. And also some of the contributors are important researchers. So it's a totally trustable library for doing this type of analysis. So let's go, loading. And then I made a function to load here my data. We will start with the eyes open dataset. So I put two datasets containing the same task, and first I was doing it with my eyes open and then with my eyes closed, and there are differences you will see. So it's important to acknowledge them. The first thing that I usually do is plotting the trigger. The trigger is the command that we send to mark the events in the data. And you can see that when the value is 2, there are more. This is the non-target. And when the value is 1, there are only a few data points. Those are the targets. This is a typical oddball paradigm. So basically presenting targets that are scarce in a set. This creates a very strong P300 wave. So it's based on the improbability of the event. So when the subject sees, or in this case, listen to the different sound, then the P300 is way stronger. So in this case, I was listening to several beeps, all the same, and every now and then there was a different, stronger beep that was, in this case, triggering the P300. And also, I like visualizing my data frame. So data are divided into columns based on each channel, and each row contains one sample. So with a sampling rate of 250 Hertz, that means that I have 250 points making up for 1 second of recording. So this is really important to keep in mind when you are working with your data. You have to know your sampling rate to understand how to epoch the data. And then in the last channel, the stem is exactly the trigger. So what we just visualized a moment before. So with this function, you can actually convert data from this format, data frame, into a raw MNE object. So the raw object is where you start with the analysis in MNE. And you can also change the setup of the device. So if you have a different device with more or less channels, you can change it here. And sometimes, not in this case, but you may need to recompute the trigger values. Sometimes the values can be -1 and 1, and for MNE, negative values are not acceptable. So the first thing we do is computing the power spectral density, plot it. So this is a representation of the frequencies in our signal along all the recording. So you see the power on the y-axis and the frequency in the x-axis. And it's very normal to have this type of artifacts caused by the power line frequencies. So 50 hertz, 100 hertz. In the USA, it's 60 hertz. So we have to do some filtering at this point. How we do it? So the first thing we want to do is to copy our raw data into a different object, because these filtering methods are in place, meaning that if you don't want to actually work on the raw data, because maybe later you want to pick them for other type of visualization, you should do this. Otherwise, ignore, but until you save, like you never save in place on the same file, so don't worry. This is only temporary until the notebook is running. So first we want to apply, as I said, 2 filters for the power line noise. They're called notch. And then we apply a bandpass filtering between 1 and 40 hertz. Exactly. So you see that the noise of the power line has been removed. We also removed most of the gamma waves and most of the delta waves. That's usually the case unless you're studying movement. So movement and some higher cognition functions are in the gamma waves, but so are many artifacts due to this type of tasks. And others study sleep, and sleep is usually in delta waves, but delta waves contain large drift artifacts. So if you're not sleeping and you're actually doing some tasks, delta waves normally do not contain useful information, so we get rid of them. And now we have to mark the events. So basically converting our trigger array into a format the MNE can understand. So I'm assigning 2 labels, non-target and target, to the values, right? So 2 and 1. And then I'm assigning also red color and green color. And since this is an interactive plot, you can actually go through all the data. So it's 1 minute of recording. You see the red strips are the non-target events, and the green one are the target events. So this is very handy, and you cannot do it with a static plot. You can also do an extra thing. They have a function in MNE that if you click on the channels here, you mark them as bad. So you can basically remove them from the analysis. So this is useful when you have a very noisy channel, but I'm not going to do it because my goal here is to prepare you for online BCI. And normally in online BCI, you cannot visually inspect the data and apply some correction. You have to use some heuristic on a software level. After doing this, we can use the event that we just put into our object to create epochs. So epochs are basically time windows. So it's the same data, but now it's divided into a lot of little splits. So every split, it's basically a second long. And it's the event deciding the beginning, right? So this is necessary when we want to study the onset of an event. And here we can mark bad epochs. So same way as the channels, we can exclude epochs from the analysis. All right, so I'm now gonna restart quickly because I will disable the interactive plot. I don't need it anymore, and later I'm gonna plot a lot of stuff, so it's better if I don't use it. To disable it, simply uncomment the inline and comment this. And now your data, yes, I forgot the percentage symbol. There it is. And then it's basically the same, but the plots are now part of the output of the Jupyter notebook, so you cannot interact with them anymore. Load, I will avoid this. Filtering, nice. All right, so we have now all the epochs as before. So now we can choose how to visualize this P300. So I'm expecting to find it after the event called T. So if I leave T and run this function, I'm going to create an average across all epochs and showing you for each channel the P300. So you see the onset of the event is at 0 seconds. The P300 is supposed to happen after around 300 milliseconds. And you can see that depending on the channel, you have a more or less strong response. So in some channels, the response is very strong. In others, it's less strong. But nevertheless, I also marked other ERPs that can be interesting. So like the P200 or the N400. And so if you load data from other tasks, this visualization will still be useful for you. So it's not necessarily tied to the P300 task. And if we plot the non-target, you will see, or you should see the difference. So 300 milliseconds after the onset of the event, there is not a clear peak. There are many peaks, but not a clear peak here. And there are other peaks in the data as well that can be explained. For example, a negative 100 can be related to the expectation of the event, but then the event does not happen. So anyways, for a classifier, if we pick this slice of data for classification, it's pretty obvious where there is a P300 and where there is not. So that's pretty much how it works. I also applied in this step a baseline correction. So I count as baseline all the time before, and then I applied this baseline to the data, basically rescaling the data. That's what it does. So I still choose to go with target now because that's what I want to do. I now pick 3 of these channels to show you in depth. So this is from the front channel. So in this case, we also have a P300A and B. So there are 2 components of the P300 that are visible. And you can see a little N200 and a little P200. And that it's not obvious that they're visible on each channel. So because depending on the position of on your head, the P300 and the other ERPs might be stronger or weaker. And this is CZ, right? So as you can see, there are some differences. Which channels to pick is basically up to you during the classification. So you can first start with all of the channels and then systematically exclude those who do not contain enough information in your opinion. But I always recommend starting with all of the channels that you have at disposal. And then I want to show you a different way of visualizing the P300 using the Morlet wavelets. So this is basically a time frequency representation, and it looks more like an image. So the power is expressed as color. So it's basically a color map. And frequency, of course, you can see that the power above 16 hertz is basically not existent. So when filtering, actually, you can change the window of the bandpass between 1 and 20, and it will still be fine for this task. And this represents the onset after the event. So we have a clear activation. So it's even clearer probably than the previous plot. And if I plot the non-target, you will see that this activation will not be present, or it will be way smaller. So not a P300 for sure. And I wanted to show you this because there are many ways to do classification of the P300. And depending on how you want to approach the task, you may even see it as an image classification. So you can extract images from the Morley wavelet and use it in a classifier, like an image classifier. And that will still be valid. Like you don't necessarily have to extract features that are similar to a time series. You can also reframe your problem in a different way. And it's been used in research by other researchers, so it's kind of a valid method as well. And finally, for the last part, I want you to visualize the topographic maps, so with the power spectral density. These plots usually help us understand which channels are more relevant and also which frequency bands. So in this case, we don't have much in the delta. We kept between 1, I think, and 40. So we have a bit of gamma, a bit of delta, but they could be easily excluded, as we've seen before. And so most of the information is in the theta, alpha, and beta waves. Also the positioning, it seems like that front and central position are way important, but also the occipital. Occipital normally is more used in a visual P300 because it's where the visual cortex is, and parietal is or temporal is closer to the auditory cortex. So you can also pick your channels based on how you stimulated the person. In this video, we have seen how to analyze the P300 starting from raw EEG data using the Python MNE library. If you like the video, hit the like button, follow the channel. In the next video, we're going to see how to use the scikit library to do a simple classification task using this data. So stay tuned.